Hello, I'm Sunny Williams. I'm up here on the International Space Station. Now, I want to say where we are. So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. It's actually on the left-hand side. If I was the International Space Station and I was flying through space like this, my left hand would be where the Japanese laboratory is. So now again, we're on the right-hand side, all the way on the right of the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. And here we do a lot of our medical experiments. So this is Node 2. This is a really cool module. Of course, most of these modules you'll see they have 4 sides and they're put together. That way we could sort of work on a flat plane, either a wall, a floor, another wall, or the ceiling. But you know, again, all you have to do is turn yourself and your reference changes. The reason I'm bringing that up is because this is where 4 out of 6 of us sleep. And so people always ask about sleeping in space. Do you lie down? Are you in a bed? Not really, because it doesn't matter. You don't really have the sensation of lying down. You just sit in your sleeping bag. So here's one sleep station right here. I'm going in right now. You can follow me if you want. So I'm inside. It's sort of like a little phone booth, but it's pretty comfy. I've got a sleeping bag right here that we sleep in, so we don't have sort of like a little bit of a cover. We don't fly all over the place. But you know, you can sleep in any orientation. I have it feeling like I'm standing up right now, but like you saw, I'm on the floor. But it doesn't matter if I turn over and I sleep upside down. I don't have any sensation in my head that tells me that I'm upside down, so it really doesn't matter. The sleep station is also like a little office. We've got a computer in here. As you can see, we've got a couple little toys. I've got some books. I've got some clothes and other things that make it sort of like home. I'm coming out. And just for reference, that's one sleep station. This one's another. Right here. There's one on the ceiling, if you want to call it. Right here. And then there's a 4th on the other wall over here. So all of us sleep in a little bit of a circle. All right, come on back. There's more to show you. Here we are in the U.S. laboratory. Again, this is a laboratory with science experiments on all of the walls here, all sorts of stuff that we do. And one of the things we also do is we exercise. We have some exercise equipment on board the space station. We need to do that because we lose bone density and muscle mass while we're up here, and that's a result of not having to fight against gravity. So how we keep ourselves in shape are with a bike, a treadmill, and a weightlifting machine. This is the bike. You notice the clip pedals. So all you need to do is actually clip your feet in, and then you can start pedaling. You don't need a seat because you don't sit down. Actually, I haven't sat down for 6 months now, so you don't need any type of seat. Just make sure you're held in with your pedals. You probably see that the bike bounces around a little bit. As I move it, it's not steady and held to the wall firmly. And the reason for that is the space station is pretty big. You saw that there's also solar arrays on the space station. If we start putting any forces into the space station, it's going to make those solar arrays bounce around a little bit. So to prevent that, the machines bounce around a little bit, move around a little bit. And that way we don't put any forces onto the structure of the spacecraft out to the solar arrays. All right, a little farther on. Come on. here's a pretty cool place. This is sort of like in your house where everybody meets in the morning. After you wash your face, brush your teeth, you want to find something for breakfast. And this is our kitchen. You might notice there's all sorts of foods here. It's like opening the refrigerator. You got all your different stuff that you want to have: drinks, meats, eggs, vegetables, cereals, bread, snacks, and that's a good place. That's where you find all the candy. Side dishes, and then some little power bars just in case. So we have all this type of food. Some of it is dehydrated, and so we have to hydrate it, fill it up with water. Some of it is all ready-made, and then all we have to do is heat it up. So something like this, I'm pulling out barbecued beef brisket. Pretty yummy. Not only is this food made in the U.S., but we also have food here from Japan. We've got Russian food. As you can see, all these red containers are filled with food that's from Russia. And then we get some of our specialty stuff, some things that we like, some of our favorite stuff that your family can send up. In fact, I like fluffernutters, and so I got sent up some fluff so I could make my fluffernutter with peanut butter. So you have a lot of food up here, no problems. I'm here with my two buddies in the airlock. Actually, these are two space suits that are ready, primed up to go outside, as we call it, to go do a spacewalk in case we have to do anything outside. Some of the things we do outside are just like inside, repairs. We have a lot of electrical boxes and machinery and solar arrays, in fact, that I talked about earlier, that are outside, and sometimes they don't work quite right. Remember, space is really cold and really hot, and it's also the vacuum of space with no pressure, and so some of the equipment doesn't work well all the time. So we might have to go out and do a spacewalk. Right behind me is actually the hatch that you go out into space, and right now we have it filled up with a couple other spacesuits because we've got 4 of them up here and some of our tools. But right behind here is the hatch in which you actually go right outside into the vacuum of space. The spacesuit is pretty big, as you can see. It's like being a football player. Part of the reason it's so big and bulky is because of this backside, this backpack. It's like going on a hike with a backpack, but the backpack and the suit weighs about 300 pounds. Luckily, in space, nothing really weighs anything, so you don't feel that it's so heavy. But we need to have such a big suit because that guy back there is essentially the heart of the spacecraft. I call this actually a spacecraft. It has all the oxygen for you. It has all the carbon dioxide removal system for you. It also has a heating and cooling system to make sure to regulate our body temperatures while we're outside. It also has a computer, so it tells you on a display here if there's anything that's going wrong with the suit, if we're running out of oxygen, if we have too much carbon dioxide, or any type of electrical problem. So it's a pretty awesome little spacecraft, and actually got to go out, use my little spacecraft a couple times, and it worked like a charm. Lucky that it works very nice. You might want to see what the helmet looks like. It's pretty cool too. We don't usually go out like this, so you usually can see when the helmet's open. So you can see what it looks like inside. Somebody's little head would be inside of here. So you can see, you can turn your head all the way around while you're inside of there, but the helmet stays still. So that's determines how far you could see. And it's usually pretty sunny out there, so we have to wear our sunglasses, and this is our sunglasses right here, which make you look pretty cool. Here we are at the throne. This is awesome. You might see the little, you might have noticed the little moon on the outside. This is our orbital outhouse right here. And of course, it serves for 2 functions. Number 2, right here. I'll show you. But you see it's pretty small, so you have to have pretty good aim, and you be ready to make sure things get let go the right direction. And it smells a little bit, so I'm closing it up. And that's, of course, for number 2. And this guy right here is for number 1. So they're sort of two slightly separate functions, but you can do a little, essentially both, by hanging on right here and doing number 1 and number 2. I might add it's color coded so you really don't get it mixed up, which is nice. This is yellows for number 1. And also there's a selection of paper. People always ask about toilet paper. What do you do with toilet paper? What kind of toilet paper do you have? We have gloves just because sometimes it does get messy. We have some Russian wipes, which are a little bit coarse if you like the coarse type of toilet paper. We have some nice tissues, which are nice and soft if you like soft toilet paper. We have Huggies, just for any cleanup. You know, we were all babies once, and this sort of helps. And then if things get really out of control, we have disinfectant wipes, just to make sure we clean up here. Because, you know, just like the water I showed you, the number 1 stuff can sort of go all over the place if you don't aim correctly. And did I mention both of these have a little bit of suction, so they should keep things going in the right direction. But like I said, sometimes things get a little out of control if you are out of control yourself flying around. So we have lots of protective stuff. And of course, you do have your privacy. Here's a little door, so other people know that you're in there. Now I'm going to take you to one of the coolest places on the space station. It's like a glass-bottom boat. This is the cupola. It sticks down below the space station. It's one of those places you find yourself hanging out in all the time because all you want to do is look back at our planet. I think some questions I had were about what do you do in your free time? And you can't help but want to just come to the cupola and look outside as much as you can. And a lot of folks, I play this game with myself about where we're flying over the Earth. Try to come in here and just guess. After being here for a little while, you can sort of figure it out. You can tell different cloud types over different continents. You can tell different soil types over different continents. So let's see. And then, of course, there's a lot of ocean. So usually we're over the ocean at first glance. I will tell you in just a moment where we are. There we go. So right now we are right over Africa. It's a little bit cloudy, as you can tell, but we're right over the continent of Africa. Hey, what's that? I think that's a Soyuz spacecraft. That's the spacecraft that's taken us home to planet Earth today. Oh my gosh. We might have to go take a look at that. That's pretty cool. It's a little bit smaller than the rest of the spacecraft, the space station, so you'll see if we go there, it'll be a little bit more crammed. But we're going, you can look all the way back to the back of the spacecraft, which is where the Russian segment is, and then you could look all the way forward to the front of the spacecraft, where the Japanese laboratory, the European laboratory, and the American laboratory. Hey, one thing I didn't show you, or I talked about but I didn't show you, was the exercise, another piece of exercise device. This is what we call the ARED, and with this you can lift weights based on vacuum in these cylinders, just like you do at home at a gym. For example, if I wanted to do a squat, I could do it like this. Oops. I should need some weight on this thing. I'm not lifting with anything, so it's too easy. One of the cool things you could do things that you can't do at home. For example, single leg squats with just one leg, because the other leg, you won't fall over. So all sorts of stuff. You can also do bench press. We have a bench that we could add on here, so you can work on your beach muscles. All right. I showed you the Soyuz. Let's go check it out. Hey, Aki, what are you doing down there?
Crashing things.
This is one of the cool things about space, too. It sort of looks like there's a big old hole here, but you don't even think twice about it. You can just jump over the hole, or if you want, you can go jump into the hole. I'm coming down. Woo! Then you can come right back up again, like Superman. Woo! We're lucky we have a really cool big space station that you can fly around in. That's actually called the PMM. You might have saw it out the window. It's a big silver canister. What's really great about that is it's essentially our closet in our pantry, or whatever you want to call it. We have extra food down there, we have extra clothes, we actually throw the trash out down there. So it's nice and organized, and we have all of our stuff that we need while we're working in all these other modules all stowed in this location down here. And it's a lot of fun to play in. Now that's a lot bigger than the Soyuz. Oh, one thing we need to show you is our patches here. While we've been up here, we've been Expedition 32 first, and then just recently we're leaving. We were Expedition 33, and there's all the crew members who are up here with us right now. Myself, Yuri Malenchenko, Aki Hoshidi, if you can read Japanese, Yevgeny Turelkin, if you can read Russian, Oleg Novinsky, and Kevin Ford, who just took over as the commander of the space station and will be the commander for the next couple months. And he, by the way, is behind the camera right now. So you can say, hi, Kevin. So we're going into the Russian segment. Be ready. You don't need a passport either. It goes a lot farther back than this. We'll go take a trip and say hello to the boys down there in just a minute. Well, let's do that first, actually, and then we'll go down to the Soyuz at the very end. This is Yevgeny.
Hi.
Doing a little tour. This is the FGB, and what's cool about this module, it is actually the very first piece of the space station that came up in 1998. The space station has been around for about now manned for 12 years, but it's been up in space for about 14 years. And this was the very first. It is like the Russians' PMM. It has a lot of storage, as you can see. So here we are in the heart of the space station, really. This is the service module. This is the central post. In case we had any problems, I know a couple of the questions were about what type of things do you have to worry about. And some of the things we have to worry about in space are fire. If we had a fire, if we had a depressurization, like we were hit by a micrometeorite and it made a hole, or if we had some type of toxic atmosphere. We use ammonia for our radiator, so there is a possibility that ammonia could come into the vehicle, and then it would be bad for all of us. If we have any of those problems, we come right here, which we call the central post. It is the main heart of the space station. It was also the first computers that came up here that ran the space station. And so behind this wall right here are these main computers. So we gather here as a group of 3 or 6 and then figure out how we're going to either fight the fire, patch the hole, or solve the toxic spill. And what's cool about this module, of course, it's the central post. It also has great windows right down toward Earth. It has controls to fly in visiting spacecraft if they need some assistance right here. It has Russian computers as well as American computers to help us control anything we need to on the space station. It's a couple of our crewmates back there, Oleg Novinsky on the right and Yuri Malenchenko on the left. And there's also a second bathroom here, which is really cool because 6 of us going to one bathroom is really tough. And so there's one bathroom here and one bathroom on the other side where I showed you. And you can probably see on the wall behind Oleg and Yuri some of the heroes of the space program. Korolev, Sergei Korolev, who was a chief designer of putting men into space. And of course on the right-hand side, Yuri Gagarin, the first man to go into space. So just reminds us of our roots. gonna stop here just for a quick second. You can see on the Russian spacecraft there's also other modules that stick out, down, and above. Right here is, let's see, I'm trying to be oriented. That's a place where we do spacewalks from for the Russian side. There's Russian spacesuits in here, and also a visiting vehicle which brought fruits and vegetables and becomes a trash container when we undock. Up on this side is also a future place where they're going to do spacewalks from, and connected to it is Kevin's, Oleg's, and Yevgeny's Soyuz spacecraft. And now let's go see ours. О, извините,
No problem.
это пробка. Coming down. Tricky getting in here. This is the docking probe right here, this big thing. This helps us connect to the spacecraft. This probe actually sticks into this cone, and that's how the spacecraft, our Soyuz, becomes connected to the ISS initially. That is then replaced by clamps, which are around here, that will allow the two spacecraft to be stuck together. And then you can remove the probe and the cone. You okay? All right, so here we are in the Soyuz. This is what we call the BEO, the living compartment, Bitovoy Otsek in Russian. It also has a little bathroom. It's not as good as the other bathrooms, so we try not to use it too much. It has drinking water in it if we need something to drink. And then, of course, it's filled up with a lot of cargo for us bringing up and also bringing back down. It has a second purpose when it comes back to Earth. It serves as a garbage container. During the descent, we'll get rid of this area right here, and everything that's in it will just burn up as it's coming into the atmosphere, so that way we can get rid of a little bit of trash. But the main area where we were on launch and where we're going to be on descent is down here, because we're not part of the trash, so we're in a safe place. So we're in the descent module, SA. It's a little small, but you can get in. Not sure how well you could see in here. Hold on for a second. I'm going to turn it up this way, just so you could see the hatch, and you could see Kevin. It's a little bit small, but we'll come in and show you around. Just starting to get ready. We're preparing a couple days ago for our ride home. It's a little bit squishy, but everybody asks, how do you sit in the Soyuz? And you sort of sit in your seat like this. The seat is molded to your body, and so you can just sort of squish in here and be pretty relaxed. Everybody has a handmade seat for them. And then, of course, there's a control panel, and that's where we do most of our actions and work right here. There's hand controllers, which you can fly the vehicle with, and there's a stick right here, primarily used for communications when we're trying to talk to the ground. So 3 of us fit in here. Like I said, it's a little squishy, but somehow it seems like we all managed to get in here and fit pretty well, and it's a pretty safe ride home. You're probably wondering, what's all this junk behind us? Well, it's all of our parachute, first of all, and then it's all of our survival gear, just in case we end up landing in some strange place on the planet and nobody's there to rescue us right away. We have all sorts of survival gear with us, keeping us safe in here. So they've pretty much thought of everything. And we'll be home on the planet within the next 12 hours. Pretty shocking.
NASA Johnson style. Johnson style. Welcome to NASA's Johnson Space Center. We are coming in hot, so don't burn up as we enter. We do science every day that affects your daily life. Throw them up for manned spaceflight. Science everywhere as we engineer the marvels that fly through the air and take us way beyond Earth's level. Science everywhere because we engineer the marvels that fly through the air, flies us through the air. Control the mission out of Johnson. This is ground and this is space. Tell me, Houston, what's the problem? It's okay, oh it's okay, because the flight controllers on the job today. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, Science Navy. NASA Johnson style. Hey, it's amazing. NASA Johnson style. Orbiting Earth International Space Station, where we work and live in space with a crew from several nations. Got Japanese and Russians and that European charm. Throw 'em up like the Canada arm. Kicking out research. 29K cubic feet revolves around the Earth. Science microgravity revolves around the Earth. Columbus jamming destiny. Kicking out research. Kicking out research. Train the Astro, not to Johnson, to go to space, to go to space, cause the missions of tomorrow start today, they start today, as we engineer the future day by day. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, Science Navy. NASA Johnson style. Hey, it's amazing. NASA Johnson style. Ryan Moore, SLS and PCV, we cannot feel the floor, cause the lack of gravity the destinations are. An asteroid, Mars, or the moon, we are blasting off. Start the countdown soon. Ignition sequence start. 6, 5, 4, 3, 2, 1. Hey, Science Navy. NASA Johnson style. Hey, it's amazing. NASA Johnson style.
Well, not our usual beginning to a meeting. I hope you enjoyed that. Got the blood moving. Welcome to the March meeting of the Ottawa Centre RASC. Got things moving on. Well, we can play it again during the break. All right. Well, welcome to new members. I know there's a few new members there. I talked to a few just before the meeting, so welcome one and all, and welcome visitors. We've got a really good program for you tonight. We've got some excellent talks. I'm not sure if our friend Gary's here yet. Gary, did you make it? Ah, he's late. Okay, so we're going to move Gary off. Did I hear Gary? No. Okay. we're going to move Gary off until later on. Can we run? So we're going to depart from our usual format since Gary is hopefully on his way here, and Al, we weren't sure whether Al was going to join us tonight because he was just flying in from Yellowknife. But he is here, so Al will run you after the break. And without further ado, because our program is a bit packed tonight, we're going to jump right into our first talk. Our own Simon Hamner is going to give us some real eye candy on the Lunar Reconnaissance Orbiter. So, Simon, take it away.
Okay. You know, as amateur astronomers, we tend to have a bit of a schizophrenic relationship with our nearest celestial neighbor, our own moon. Some among us even consider the moon to be a source of light pollution that degrades our views of faint deep sky galaxies and nebulae. But there are others who like to observe the moon's surface, following the passage of the shadows that emphasize the definition of many of its most interesting features, ranging from impact craters to valleys and to cliffs. But we tend to treat the moon as a collection of curios, or worse, as a catalogue. A collection of stuff to be observed and checked off on a list of items whose origins we may not really understand, no matter how much we go back and look at these things. Next one, please. There are many publications available to guide us on our exploration of the moon. Personally, I started with Ernest Cherrington's Exploring the Moon, which was first published in 1969. I was a little late in discovering Antonin Ruckel's Atlas of the Moon in its 2004 updated version. It's a magnificent roadmap to all things lunar, but that's all it is. It'll guide you geographically, but it doesn't explain what it is you're looking at. Even the RASC's Williamson Lunar Observing Program, despite its geological introduction, which I had a hand in editing, it still takes a find, observe, name, catalogue-style approach to the moon. I think that the best moon books available today are still planetary geologist Chuck Wood's The Modern Moon, published in 2003, and the Kaguya Lunar Atlas that he co-authored in 2011, and I have a copy of that one here with me if anybody wants to see it during the break. Now, these books are not so much atlases. They're more of an investigation of what's been going on with the lunar surface for the past 4.5 billion years, with an emphasis on interpretation and understanding of process. And by process, I mean geological process. So when the RASC National Discussion Group was recently all a Twitter with news of Chuck Wood's latest offering entitled 21st Century Atlas of the Moon, I sent in my order. Now, for me, the most attractive aspect about this new atlas was that it was announced to be based on the spectacularly high-resolution imagery that NASA's Lunar Reconnaissance Orbiter is still sending back from the moon on a daily basis. And when I say spectacularly high resolution, I mean it. The best resolution images they're sending back are 0.4 meters per pixel. I was disappointed. Now, don't get me wrong, this is indeed an excellent atlas of lunar features for amateur astronomers, so they can seek out features from their backyards. However, the Lunar Reconnaissance Orbiter photographs are the ones that are used as the broad-scale locator images for navigation, while the detailed images to guide observation are mostly taken from older missions with lower resolution than those that the Lunar Reconnaissance Orbiter camera is capable of. So I asked myself, what do I expect of a truly 21st century atlas of the moon? When I discussed this with the fellow members of the Ottawa Valley Astronomers and Observers Group, the OAOG, at their last February meeting, the 30 to 50-year-olds, remember that, 30 to 50-year-olds immediately pulled out their iPads and went online to investigate the LRO images that I was discussing with them. That's exactly what a teenager or a 20-something would do as well. So I think that a 21st century atlas is really something that utilizes all the tools available to amateur astronomers today in order to help them better understand what they're observing through their own backyard telescopes. Let me put this philosophy into a tangible perspective. If I were to ask you, what do you imagine the lunar surface looks like if you were actually standing on it? And most would probably reply, pretty dusty. And if I asked you, what do you imagine the interior of a small impact crater looks like if you were actually standing in it? I think most of you would reply, pretty smooth. And if I was to ask you, what do you imagine the central peak of a complex impact crater looks like if you were actually standing next to it? And I think most would reply, a mountain of solid rock. The detailed LRO images, LRO, Lunar Reconnaissance Orbiter images, publicly available on the web would show us that even if we can't see that sort of detail that the LRO can through our own telescopes, our perception of what we think we're seeing through our own telescopes is commonly wide of the mark. So what I'm going to do here is I'm going to run a selection, just a selection of detailed, very high resolution lunar reconnaissance orbiter images by you to give you a taste of what they can show you and how they will positively impact on your own lunar observing experience and understanding of what it is you're actually looking at. Now, each slide will have a lunar location inset in the top right corner to help you place where we're looking. So let's start with impact craters. Next one, please, Chris. Now, here's the central peak in Aristarchus crater. There's the central peak right down there. And it is indeed made of solid rock. In fact, you can clearly see that it's made of compositional layers. See the dark layer, white layer, gray layer here? Made of compositional layering in the peak, as well as in the terraced wall in the background. Look at the layering here. See that dark layer there? And then a white layer there, and then more white over here. So we're clearly looking at solid rock there. Next one, please, Chris. But here is part of the central peak on Tycho crater. And it looks pretty rubbly. Note the scale bar up here. That's 200 meters. Notice also the 130 meter long boulder that's sitting on top of the peak at this location. We're at 2 kilometers above the crater floor here. Next one, please. Well, here's the summit of the central peak of Bullialdus crater, and this is just a pile of rubbly boulders. This isn't the whole peak, this is just the highest point on it. But what's this smooth stuff here that's surrounding it, and in fact even seems to be on some of the bouldery material? Is it really dust? Next one, please. Well, here's a clue on the floor of a small crater known as Linné F. Again, note the scale bar, that's 200 meters. And you've got a central mound here in the floor of the crater. And it's surrounded by a smooth moat of impact melt. That's this medium gray material here. This stuff out here is the base of the crater wall. And that impact melt is a continuous sheet of molten rock that was generated by the heat of the impact that formed the crater, and melt which then fell back into the crater cavity and pooled on the crater floor. You might notice these house-sized boulders around the edge here of the impact melt pool. Next one, please. Now, how do NASA scientists know that this smooth stuff is in fact impact melt and not dust? Well, here's a sheet of the smooth stuff on the lip of the crater Olcott. And this is on the far side of the moon. Note my convention for far side of the moon. You can see the near side with a cross on it. Now, the crater itself is to the top, and this is the external shoulder, if you will. And notice these lobes and this smooth, dark material here. In fact, that lobe there has even broken as material started to try to slide down the slope. But look at this tongue down here. I'm afraid it's in the lower part of the image. I can't do much about that. But that clearly has flowed. That is melt. Next one, please. Now, here's a sheet of impact melt, this smooth gray material here. It's on the floor of Thales crater at the base of the crater wall. The crater wall is back here, and this is the crater floor. Now, notice the house-sized boulders, these ones over here. And some of these are even quite large too. There should be a scale bar on this one. No, I forgot to put one on this one. They are house-sized, sort of 30 feet across. And notice how they're absent as you come even closer to the floor of the crater. Notice also these squiggly channels here. They're all over the place. These squiggly channels, all of which seem to be pointing down towards the floor of the crater. And they're running over the surface of the smooth impact melt. We'll come back to the boulders in a minute, but meanwhile, let's look at channeled impact melt on the moon. Next one, please. Now here are branching fingers. Down is this way, this is upslope, that's downslope. These are branching fingers of impact melt, which are flowing over a bouldery surface. These are the boulders, you can see them very clearly. There's the scale bar, so these again are house size at least. And this is on a surface adjacent to a Grotrian crater. Again, note the scale bar. This is a very detailed image. Next one, please, Chris. And at the same scale as the previous image, this is a single-channeled flow of impact melt near crater Ingalis. Here's the channel of melt. But notice the details. The flow is flanked. You can particularly see it well on the southern side here, but it comes around that side as well, but it's really nicely shown here. It's flanked by boulders up to 10 meters and more, which the flowing melt, which was flowing this way, has actually shoved to one side. And if you look at the termination, you can see that there are multiple lobes. There's a lobe there, there's another lobe there, and another lobe there. So this impact melt was not just flowing, it was flowing in pulses which actually pushed through the older terminations of the earlier pulses of flow. And we're talking about stuff occurring in space of minutes here. Next one, please. This is a little dark, but it's good enough. This is an example of channeled impact melt flow from Lowell crater, and it nicely illustrates this concept of a second pulse of melt flow. You can see there's the original flow, and then here is a new lobe forming, either because the impact melt was breaking through the old flow, or maybe it flowed over the top of the old flow and then formed a new termination. Next one, please, Chris. Now, not all that flows on the moon is necessarily melt. At the same scale as the previous images, there's 100 meters scale bar. This is granular flow of sandy to gravelly debris running across the side of Pythias crater. Well, we can also see layering here. That's down, by the way. Downslope, upslope. And you can see layers here, which are actually the layers of the individual basalts, which went to fill the mare. More on the basalts later. But remember, this is dry flow. There's the source of the flow. Here's the gravelly material which flowed and cut a channel through these layers of basalt. And then when it got down to the crater floor, the material slowed down and it formed a fan, a debris fan. But remember, this is dry. There's no water involved here. Next one, please, Chris. Within the small crater Clavius E, which occurs within the larger crater Clavius we know so well, we see this remarkable example of fine-grained debris that has flowed in a channel over the top of older bouldery debris. Here's the bouldery debris. You see it looks so pimply, but in fact it's in relief. And more bouldery debris here. And you see these fingers at the end of the fine debris flow. There's the debris flow itself. It's got very few impact craters in. There are a few. And these are very young, and NASA is asking itself seriously whether these debris flows are forming today. I'll admit that this one's not easy to distinguish from impact flow. Next one, please. Here on the walls of Gardner crater, these walls are plastered by multiple braided fine debris flows. The smooth material in the medium gray, you can see it here. You can see them all through here. These are braided fine-grained debris flows that appear to cover older, coarser-grained debris flows. You can see the coarse grain here, and you can see it looks granular up there. Those are boulders. There's 100 meters. So you've essentially, from the same impact, you've got boulder debris flow being ejected from the crater, and you've got this fine-grained debris flow as well. Next one, please. And this is a glorious example from Furnarius crater where very narrow, fine-grained debris flows, that's upslope here, downslope here, there's the crater floor. There are literally, every one of these streaks is a fine-grained debris flow. There are hundreds of them. And they're draped over a boulder apron, as you can see here in the lower slopes of the crater wall. That's just a carpet of boulders, somewhere in the 10 to 20 meter size. And then down on the floor of the crater, you can see even coarser boulders again. Which brings us to look at lunar boulders in general. Next one, please, Chris. Now this right down here, this house-sized boulder has bounced its way all the way down the central peak of Schiller crater. You can tell it's bounced because it's actually jumped from pit to pit to pit to pit to pit. I don't need to say anything more about that. Let's move to the next one. And these curved trails here, you can see them there, and then there's two here, and there's another one over there. These are down the wall of Picknell crater on the far side of the moon. These clearly rolled without bouncing. See, they're continuous trails. Next one, please. And this one I like. This 10-meter plus bouncer here rolled all the way down slope, and then it did a hole-in-one in a pre-existing hole. Notice the scale bar up here. This is pretty good stuff, you know. I mean, look at Look at the detail on these house-sized boulders, which are confined to the base of the slope. The reason this one rolled so far is that without any air, the thing that determines how far and how fast something will roll, is essentially a matter of its kinetic energy, which is a function of its mass, which is a function of its size. So the big boulders actually roll further than the small ones. Next one, please. Boulders are everywhere on the moon. Remember my question about what the interior of small craters look like? Well, this one near Reiner Gamma has a central pond of impact melt. There it is, right down there. There's the exterior of the crater, okay? That's the crater wall. And it is absolutely blanketed inside the crater with boulders that fell back from its impact ejector. I don't think that if you were looking at that through your telescope, you'd expect to see something with a bouldery carpet quite like that. Next one, please. And this one I really like. Personally, I'd always simply assumed that ejector rays, you know, the bright streaks that we see radiating from impact craters like Tycho, I'd always assumed they were made of dust, until I saw this image of an ejector ray from a crater within the Mare Moscoviense on the lunar far side. Look, there's the scale bar. These boulders are going from 50 meters to 10 meters, and that is the proximal end of this ejector ray. What did you think they were made of before I showed you this picture? Okay, let's turn to lunar volcanism, starting with the Mare basalts that fill the up to 1,000 kilometer across multi-ring impact basins that we can see on the lunar near side and we're so attracted to. Next one, please, Chris. So here we're looking at the wall of Bessel crater, and we see these fine layers. You can see them here. And there's the scale bar, about 100 meters. And each one of these represents an individual basalt lava that contributed to filling the Mare Serenitatis in this case. Each flow is probably about 20 meters thick. And the cavity, the original cavity of the Serenitatis basin was likely about 10 kilometers deep. That's a lot of individual lava flows. Next one, please. I like this one. And here's the lunar equivalent of the Highway 174 nightmare. A 50-meter wide collapsed pit in the basalt flows of the Mare Tranquillitatis. The way it formed was the lava was still flowing underneath the frozen skin of the lavas here and left a bit of a cavity underneath and things collapsed, just like Highway 174. But look carefully, and what can you see in the illuminated part of the floor of that cavity? Boulders. This is high resolution. Next one, please, Chris. Okay, here's a favorite of many lunar observers, Hyginus crater and its valley segments. Again, note the scale bar here, we're up at 10 kilometers. Obviously, this image is not 0.5 meters per pixel. The crater itself, there, is not an impact feature. We know it's a hole in the Mare basalts without a raised rim. And in fact, it's a volcanic caldera, which means it's a collapsed volcanic vent. That's nice, but the thing I like about this picture is notice these pits all the way through this valley segment up here to the upper left. These features are related to exactly the same volcanism. And with a good telescope, you can actually make them out. Next one, please, Chris. So now let's look inside Hyginus crater at its floor. Note the dramatic change in scale here. We're now at 200 meters. And these bright things here, and this is just the biggest of the bright ones. And these are actually collapsed pits in the floor of the collapsed caldera. If you like, they're proof of the volcanic origin of Hyginus crater. This is quite remarkable. Next one, please. So by now, we're all aware that squiggly valleys are the erosional products of rivers of flowing volcanic basaltic lava on the lunar surface. And you can see them here coming across beautifully like this. They even continue up through here. There are more up through there too. However, until Lunar Reconnaissance Orbiter, I had absolutely no idea of the existence of these exceptional examples in the vicinity of the small crater Herygonius K. And this is Herygonius K. And for scale, it's about 10 kilometers across. Next one, please. Here's another favorite of lunar observers, Posidonius crater. But did you know that one of the most prominent fractures in inverted commas in the crater floor is in fact a 130 kilometer long squiggly valley carved by basaltic lava? And here it is. I say starts. It may end here. I really don't know which way things were flowing. But it's a squiggly valley which comes up like this, and then it actually hugs the floor, the foot of the crater wall. And next one, please, Chris. And finally, a perennial favorite of us all, Schroeder's Valley, just north of the Aristarchus crater on the Aristarchus Plateau. So what, I hear you say? Been there, seen that. But did you know that there's a squiggly valley running all the way down, and there it is again. I can just see it there, and I think I can just see it there, and I think I can just see it there, and I think I can just see it there. Running all the way down Schroeder's Valley, and when you get to the end, Schroeder's Valley, look, it turns and goes this way. And this squiggly thing keeps on coming. It cuts across it down to there. Clearly, the squiggly valley represents a younger event. Next one, please, Chris. Now, I introduced this presentation at the beginning as a taster to what the Lunar Reconnaissance Orbiter has to offer us as amateur astronomers through our own backyard instruments. Let me end by suggesting that the Lunar Reconnaissance Orbiter has in fact provided us and continues to provide us. They actually have new images going up every couple of days on their site. A truly 21st century lunar atlas that already can teach us how to better understand our nearest celestial neighbor. To help you find your way through the growing Lunar Reconnaissance Orbiter image archive, I've downloaded about 85 detailed images that I've briefly annotated with commentary, and I've also included the URL for each image, all of which Chuck O'Dale has now actually posted up on the RASC Ottawa Centre website on the articles page under my name. This will allow you to immediately jump into the Lunar Reconnaissance archives, actually going to looking for images where you'll find on the pages which I'm guiding you to, you'll find excellent location images and explanatory notes, short explanatory notes, which are well written for the non-expert. I'm not often very complimentary about NASA, as many of you know, but in this case, they really have got it right. So I would strongly encourage you to peruse the actual Lunar Reconnaissance Orbiter resource itself. It will literally change the way you observe and think about what you see on the moon's surface through your own telescopes. Thanks for listening.
All right, next up we have Rick Wagner, who's put his drinking habit to good use. Oh, did I say that out loud? I'm sorry, Rick. Didn't mean to let the cat out of the bag there.
Well, I guess he has let the cat out of the bag. How to combine beer with astronomy. Officially, it's how to use a pinhole camera for astronomy. So, let's see. Do I have a controller? Here we go.
The other way.
There we go. Pinhole camera. Basically, it's a little box with a hole inside of it, and light from your target shines in straight lines through and forms an image on the back. So if we can put some sort of a sensor in the back there, we can actually get a picture. So we could use a beer can. They're about 5 inches high, about 8 inches around, so 5 by 7 inch sheet of film or enlarging paper would fit inside. So let's collect a bunch of tools together. And very important, there's a beer glass so you can empty your beer cans. And tape, knife, it's all pretty much regular household stuff for the most part. So, first priority is what beer are we going to use? Well, a Caledonian 80 shilling, I highly recommend it. It's wonderful beer, really excellent stuff. Red Stripe Jamaican Lager, it's very good. Bud Light in the middle, unfortunately, that hardly even qualifies as beer. And one of the problems, of course, is you have to empty the can before you can actually use it. So unless you have a big slug problem and you need slug bait, or your composter is getting slow, and of course now we've discovered, it's a big scandal, the Americans are watering down their beer. Who knew? What a surprise. So I drank a few beers and take the lid off with a can opener, just a normal household can opener. Well, you can see what happened was it actually chewed the whole rim off the can, which leaves the can extremely flimsy, so I didn't know what to do about that. That was a bit of a surprise. So I tried a different can, and it seemed to work fine. So what I discovered with extensive research at the beer store is 440 milliliter cans and 500 milliliter cans all have the wrong top. If you look here, you can see this little beveled area in here slopes down at about a 45-degree angle in the 473 milliliter cans. That's what your can opener will dig into, and then you can actually remove the top without removing the rim of the can. This is very important. So we're going to take the top off the can and put a piece of film inside, so we need to replace the top. I finally discovered about the fourth or fifth one I made, it's better to do all the construction work while the beer is still in the can. So if you've already taken the top off, you have to bite the bullet, go back to the beer store, buy some more beer, and then try to do the work before you do the construction. So take a piece of cardboard or thin plastic and just wrap it around the top, tack it with a piece of masking tape, wrap it in duct tape for strength, trace around the can on another piece of cardboard or thin plastic, tack a top in place on there. I cover the top with electrical tape just to make it somewhat waterproof, and then I wrap another layer of duct tape around the side. I find that the electrical tape, the adhesive on it isn't very good, and it tends to come undone after a little while. So, now we can drink the beer, take the top off, and we punch a little hole in the side. It's important to mark where you're going to punch the hole because the hole is very small and it's easy to lose once you've punched it. So I used just a very fine sewing needle, push it through as even just 1/8 of an inch or 1/4 of an inch. You want to try and get as small a hole as possible. If you make too big a hole, well, then the picture starts getting blurrier. You can also make a hole too small, and diffraction starts to make the picture blurrier, but you're not likely to run into that problem here. So, the other thing it does is it creates a burr on the inside of the can. So I reach in with a pencil and a piece of sandpaper and smooth off the inside so it's a nice smooth hole inside and out. And there's a picture of the finished hole. That's probably somewhere around 1/2 millimeter in diameter. So, well, we got to have a shutter if we're going to have a camera. So you take a little piece, about 1 inch of electrical tape, fold over one end so it's got a handle on it. Oops. And then just stick it over the hole. Our sensor is going to be 5x7 matte finish enlarging paper. You want to use matte finish because otherwise you can get, I think, reflections around inside the can and it'll start to affect the images. This stuff, it's quite surprising. You think of all the work that people do in dark rooms, this stuff is very insensitive. So you don't have to worry about taking it out in daylight. Basically, stay out of the sun and don't waste too much time while you're loading up your can. So what I did, I just picked a dim corner in the shop and laid stuff out ready to go. Coil up the paper and slip it into the can. Make sure the hole isn't covered by the paper. It won't work very well otherwise. And put the cap on, put your shutter on, and we're ready to take a picture. So, find a nice view, facing somewhere from sort of east to south to west, someplace where you're going to get the sun tracking across the sky in the field of view of the camera. You remember this camera is actually going to take about 180 degree wide field of view, so it's not very critical where you point it. So I just hung mine on the side of a tree with some wire and left it there. Well, after a few days, I'm wondering, is it working? Did I do it right? Did I get the paper in with the emulsion side facing the light? Maybe I put it in backwards. I don't know. So it's also, by now, it's been a 260,000 second exposure. So I pulled it down to see what happened. Oop. And that's what you get. So it's almost completely blank, but if you look, there is a pale blue stripe here. So, without developing it, no chemicals, no messing around, stick it on a flatbed scanner, scan it, bring it up in your favorite image processing program, take its negative, and increase the contrast dramatically, and there's what you get. Wow, so it's actually functioning. And what you're looking at here is over several days, the sun has risen in the east, gone over the zenith or the meridian and back down, and leaves a nice trail. The trees even show up in the picture, and the islands on the far side of the lake. So this is kind of cool. Enthusiasm gets the better of us. Well, okay, so try and show a little control, not desecrate your whole property. But anyway, I did make a couple of more of them. And so this one is mounted on the side of the balcony, much the same view as the first one. You can also put them horizontal, and it gives you different distortions because of the curvature of the can. I actually taped 2 pencils on the sides of the can. I don't think it was really necessary, but it stops any tendency for the can to roll back and forth on the railing. So I had another one out for a 2.3 million second exposure. That was about 27 days. And all excited to see what I'm going to get. And I got that. This is low tech, so nothing should go wrong, but clearly something's gone wrong. Now you have to remember, these get shot upside down, of course, so it looks like something has affected the film or the paper and then run down. So I haven't figured out what that is yet. However, you can see that over the period of a month, the sun is getting higher and higher every day. You can also see the gaps. On the cloudy days, there are little gaps when it was cloudy during the day for short periods. And this gives you a hint of just how bad the weather was in February, because that's not a heck of a lot of sunshine there. So that's where it stands right now. I have 4 out right now running. That 3 of them are aiming for 16 million second exposures. Essentially, as the sun gets higher and higher and higher, it will reach its peak at summer solstice, and then it will start coming back down again, which means it'll start overlapping its previous trails. So basically, seems to me the best time to put it out is at winter solstice or summer solstice, and take it down at the next solstice. So, have I learned anything so far? I haven't figured out what this is. I put the pinhole in the height of the can. I put it exactly in the center of the can, and it occurs to me now that if the sun gets too much higher, I'm going to start losing the sun off the top of the picture. So what you could do is move the pinhole up the side of the can a little higher. Essentially, this is the pinhole version of a perspective of a $5,000 or $6,000 perspective correction lens for your SLR. And the other thing, of course, is you're not limited to beer cans. They're the best, but in theory, you could make it in a box. People have made them in film cans for little teeny ones. Cardboard boxes. It's not going to stand up very well to weather conditions, but anyway, so this is an experiment in progress, and as I figure out what's going on here and hopefully get better results, I'll come back and show more pictures in the future. Any questions?
So Rick, you said There was no processing involved at all?
There's no processing. You just take the paper out clean and dry, scan it, and invert it. The camera is actually operating at about f130, so it's slow. But on the other hand, the sun is extremely bright, and it's not moving very fast. So there's, even through that little teeny hole, there's a fair amount of light, and it's able to affect the paper even without the development. And that's why you don't have to worry about taking the thing out in daylight. For instance, loading the can in a lit room is not a problem because you're not going to be developing the paper.
Rick, I'm wondering if the heat from the sun is causing that change, that effect. The blue section is because it's at the meridian. It's just heating the...
Yeah, except that there seems to be 3 of them. So, I don't know. It might have been condensation in the can.
humidity.
Yeah,
Yeah.
so still looking at that.
I guess you need to.
We need a beer to figure that one out.
Yeah, that's right, maybe even a bunch.
Don't make the can so airtight. Let it be able to exchange the air.
That's a thought. Try to make it exchange air, but without letting any light in. But
Or put in a packet of silica gel.
yeah,
Yeah.
that's a good thought.
Have you put any coatings inside the can? The paper covers most of the inside.
Yes.
But there's a bit of a slit in the front,
Mhm.
and that's raw aluminum, I would guess.
That's possible.
So black paint or something.
Yeah, it might work. Yeah, I'm not sure if they're actually bare aluminum inside or if there's any sort of a plasticized coating, or I've never examined the inside of a beer can. So once it's empty, I recycle them. All right, thanks.
All right, Mr. Boyle, where are you? There you are. All right, you made it in. Come on up, come on up. Gary's going to talk to us about Ottawa skies.
Well, the sun is getting quite active. In fact, there's a KP6 storm hopefully tonight, but hopefully if the clouds do part, look toward the north and west and east, and you might see some greenish activity. But there is a video that NASA took of a solar prominence back in July, 19th, I think it was. And if we can run that video just for it's about a 4-minute video, but we will run about half of it because we were pretty pressed for time. And in fact, this was on the astronomy picture of the day for, I believe, Wednesday or Thursday. So if you just go back to that. So just keep watching this guy. Just grow and grow and grow. Yeah, after a bit, we can just advance it, maybe. Just move it on. Because the end part's pretty neat.
He's going to actually turn on, there's actually a soundtrack.
Oh, there's a soundtrack, great.
Yeah.
And I measured this. This is 10 Earth radii across and 7 high or something like that at the maximum. Just phenomenal. But when they say coronal rain, it actually rains down here. It's just amazing. That is just incredible. I'm not sure how long a period this was, if it was over a day or a few hours. But usually solar prominences just go up, either release off a flare or come back down. Not just hang up like that and just fall back down in this gracious display.
If memory serves, Gary, I think the whole sequence was 10 hours.
10 hours? Okay, thanks, Paul. So it's about 10 hours, the whole sequence. And then eventually fades off. It's almost like lava falling off a cliff. It's plasma. Amazing. Great. Thank you, Chris. So Pan-STARRS is coming to a sky near you, and it is brightening as we speak. It's still in the southern hemisphere. It's right next to Fomalhaut, which is, but both are below the sun, so we can't see it during the day. But next slide, and you'll see a chart. So we'll see it around starting on the 12th, of March. And in fact, the Museum of Science and Technology will be hosting, along with the RASC, a star night in front. Some public viewing, not sure what night yet, but hopefully close to any time after the 12th on to try to get as bright as possible, because this guy's really going to keep moving up. It'll lose 1 magnitude of brightness over 5 consecutive nights and move about 1 degree to 2 degrees per night. So it's really going to be moving. Next slide, please. But you can see as it moves, it also hugs the horizon, so it's not moving straight up as we saw with Cassiopeia, but kind of on the horizon. So it should be hopefully between maybe 2nd or 3rd magnitude as we can see it. And look at this on the 12th, right next to a 2% crescent moon. And then on the 13th, the moon is up a little bit. So if you can't really find the comet, look for the crescent moon. It'll be right below it. It won't be the easiest thing to see because of the solar glare. Next slide, please. And don't forget on March the 10th, spring ahead 1 hour. And also don't forget the universal time correction to Ottawa time if you're going to plan for Jovian events or anything that's in the Observer's Handbook or in Sky and Telescope magazine. And next slide. And just quickly, when is Easter? Easter this year is on the 31st of March. People are wondering, why does it change every year? Well, Easter occurs on the Sunday right after full moon, which is right after spring. So this is why the earliest it can be is March 22nd, and the latest it can be is April 25th. So Easter is the 13th, 31st, Good Friday here. So take spring, next full moon, then the next Sunday right after. That's how you figure it. And next slide. And mostly the planets are lost in the solar glare. Mercury and Venus, pretty well can't see it. Mars, very, very low. And Mars will be just a 0.7 arc seconds next to Uranus on the 22nd. But again, it's just so close to the horizon, it's not even worth it. Jupiter still put on a good show, but it is whisking away at almost blinding speed and sets at 1:30. Saturn, if it's clear tonight, Saturn actually rises with the nice third quarter moon tonight and is rising at 11:05. So now Saturn will be the showpiece in a couple of months. And if you're into Uranus, especially Neptune, whatever floats your boat. And next slide for the lunar distances. Lunation 11:16, and it's the full worm moon. Didn't make them up, Farmer's Almanac. And that will be it for this month, folks. Thank you. See you next month. So I want to see some great pictures of the comet. Take your time. Go to any far western horizon, very, very even or very, very close without trees. Even with trees, it might make a difference. Take as many pictures as possible. It could be a very, very bright comet. And you'll actually practice for ISIN, which will be at the end of November of this year. Sweet. And great beer can there, Rick. I can see it as the Sky and Telescope product of the year for 2013 for sure. For sure. Thanks.
Can I just add to Gary's comment and repeat what he said about observing the comet at the museum? The museum is going to put on an event not using the big telescope and is hoping to have a few RASC members to help out. This time they're not announcing a time or date until the last second. On a clear night, on the most appropriate night, we'll arrange it. So if you're available to help out, let me know, and then we'll coordinate by email and tell you when it is.
Yeah, so definitely I guess it'll be on the museum's website, RASC website, Ottawa, and also I'll be on the radio and television blasting when the next clear night is. So stay tuned, folks.
Open arms. All right. Put that away. All right, and you're going to grab the lights. Perfect. Okay, so we're going to jump right into our observation reports. We have a few folks this month, and we'll start out with Mr. Commission. What you got for us, Paul?
Well, we have here M103, otherwise known as NGC 0581. It's in Cassiopeia. The field of view here is about approximately the size of the moon. It's 37 by 27 minutes of arc. This particular cluster is in Cassiopeia. It's in the OB in there in the Cassiopeia Perseus area, and it's in distance. It's probably in one of the books I read. It's the farthest that you can see in the M catalog, at least. So it's fairly faint. It's about the same brightness and distance as the double cluster, but the double cluster, as you know, is separated more. So this is a different type of story. But this is a nice object. It's at 60 degrees north, so you can see it year-round. If you're out, if you have a good north view, you can see that at any time of the year. Thank you.
Thank you, Paul. Okay, Rick? That's not through a beer can.
It's a big beer can. Okay, this is just a collection of stuff I've been doing over the past couple of months. It takes me a while to get around to processing some of this sometimes. So I've borrowed a 60 millimeter Coronado hydrogen alpha filter off of a friend, and started trying to take pictures of it, of the sun in hydrogen alpha. That's one of the emission lines from hydrogen. And so you get quite a different view of the sun. In particular, you can see the prominences around the edge and filaments. That's the little gray guys there that are basically clouds of gas and dust, or clouds of gas and plasma that are in front of the disk. And then these are basically the ones that Gary was showing just a little while ago, and sunspots as well. So these are just done with an 80 millimeter refractor and a single lens reflex camera. I take one exposure for the disc at about a 500th of a second, and then about a 60th of a second another exposure to get the prominences, and then overlap them in Photoshop. This is a different day. This was the 17th of February. It's not a great picture, but it has a great story, because this group here, you can see it's quite bright around the group, and it has a filament hanging off of it. Particularly nice long filament there, and some quite dramatic prominences. Unfortunately, it was really turbulent that day, so the picture doesn't turn out very well, but this spot actually underwent a fairly significant solar flare while I was watching it. So when I first looked at it, there was actually, Alcamo pointed out, basically a really bright hairline kind of wrapped in about here, and extremely bright, much brighter than anything else on the disc. And as I watched, it gradually changed shape subtly, and over a period of probably a half an hour disappeared, and then this little filament appeared beside it. And so I thought, well, that was pretty cool. And I showed this at the Kingston group, and somebody told me, oh, that's what's known as an Ellerman bomb. Well, okay, except that I went on the internet, and spaceweather.com does a lot of stuff to do with the sun, and I went back to the 17th there to see what they had. And if we can play this video, this is actually a UV version of what I saw at exactly the same time that I was looking. And so you can actually see the flare happen, and then you can see the filament flash out down this way. And so I think this again was something over 45 minutes or an hour or something. So that was quite exciting. It's not very often you get to catch one of these things. Next image. This was actually back in December. I went down for my morning. I go down and go for a canoe ride every day before sunrise. And that morning, the lake was frozen. So I'm standing there on the dock wondering what to do, and I noticed the string of objects in the sky there, and I thought, isn't that beautiful? And it was such a lovely sunrise. So I ran up, got my camera, and after I took a few pictures, I went to figure out, what are those guys anyway? And so there they are, Mercury, Venus, Saturn, and then a pair of stars, all up in a nice line.
Didn't go swimming,
I didn't go swimming that morning, no.
Did you hang beer cans?
I didn't have any beer cans, no. This is too early in the morning, even for me. This was back on the 9th of February. Mercury at the top, and Mars is the lower one. I stood out on the ice. In fact, I went down on the ice with my camera equipment and dug a little hole through the snow so I'd have some, solid ice to put the tripod on. And the neat thing about that is 3 of my neighbors have now asked if there was a meteorite impact on the lake. But anyway, I stood there for probably half an hour taking pictures every so often. Mercury was quite visible, quite easy, but I couldn't see Mars. And finally, after about a half an hour, somebody pointed it out to me. And I was able to see it naked eye. And finally, this was the same evening, about an hour or two later, somebody was asking me that they had heard the space station was going to fly by, and I thought, I haven't looked at one of those in a long time, so I went on to Heavens Above website and checked it out, and sure enough, really quite a spectacular passage going by fairly high, nice and bright. So I went back down onto the ice with, in this case, I actually had a barn door tracker. It runs on a synchronous motor, so I need 120 volts AC to run it. So for the first time ever, I tried using one of the Canadian Tire battery eliminators with a power inverter plugged into it, and then my motor and my camera battery and my dew heaters all plugged into it, and it all worked. So this is a 5-minute exposure at f5.6 ISO 400, 255 second exposure. With this is a 10 to 22 millimeter ultra wide angle zoom shot at 10 millimeters. So it's a big piece of sky. That's Orion there. You can see Taurus is up here, the Pleiades. Sirius is down there. And basically the space shuttle just came up from the southwest, went by, and then faded out into the Earth's shadow.
The space shuttle?
Or the space station. And that's it. Thanks.
Thanks, Rick. That's some nice stuff. All right. Mr. Olson, I believe. Here you go.
The February 8th, we had a clear night, and so I got my equipment working, or mostly got it working. And then on the 9th, the same night that Rick's picture was taken of over the lake, it was a clear night where I was too, and so I decided to do some imaging, and I decided to image things that I had done before. And so I imaged M51 and 81 and 82 down here at the bottom. I just so you could recognize, this is the Big Dipper. That's the zenith right there. This is almost overhead. And tonight at 11:30, this is what you would see if you went out. Every star is a Messier object, so it's a fabulous part of the sky to sort of snoop around in if you have a telescope or you want to do some imaging. So I just went for these. I'd imaged these lots of times before. I was just trying to see if my equipment was working well. I made some equipment changes, which I'll tell you about in just a minute. Okay, next slide. I started off with M51, and this is one of my old favorites. It's actually the first thing I ever imaged. And this is picture number 47. So I'm really a boring photographer. This has been imaged by me 47 times now. Okay, next one. This is 81. A beautiful big spiral just in near the Big Dipper again. And the next one. This is 82. 82 is kind of interesting because it's incredibly active. And this area right in here is, I believe there's a black hole in there, and it's spewing out stuff across like this, which if you image in hydrogen alpha, you can actually see stuff being blasted out. This image does not have enough exposure and time on it, so I'll work on it a little later. Okay, last one here. Okay, the equipment change I made was guiding is a giant pain in the neck if you use a Schmidt-Cassegrain telescope, because there's a floppy mirror in it. And the mirror flops around and your guider never tracks very well. And they have all kinds of tricks to solve this problem. And I'm trying a different one here right now. Basically, the light comes in the scope at the front and hits a mirror here, which is a beam splitter. And it allows the hydrogen alpha light to go through to your guider. And the visible light bounces off the mirror and gets into your camera. And this, then, if the mirror flops around, the image flops around the same, both in the guider and the imager. And I'll tell you all about it next month. Yeah, thank you.
Great. Thanks, Bob. Okay. I have one image for you, which I've actually spawned into a few just because of some interesting stuff that I found. This was actually me giving a first light test to a new camera that got a QHY9 monochrome imager. And this was, again, on the same night. We've had so few clear nights, but the night of February the 17th was exceptionally clear and stable. I live out in the country there, so we had some pretty dark skies there, and I thought this would be a good first test for this camera. So this is just basically a luminance frame with just a UVI or a cutoff filter on it. Oh, what happened there? Supernova. Supernova and M101. You gotta love it. So the sky was very dark. I measured it with the sky quality meter, and it was at 21.55. So nice and dark indeed. And I chose M101 for the image because at the time I was imaging, that was passing pretty much directly overhead. So tried to get maximum clarity. And here you can see because this was on an 80 millimeter refractor, it's a nice wide field. Just an 80 millimeter f7.5 refractor. So you can see the pinwheel at the center there, and you can see a couple of its companions here. This guy. And you can just barely make this guy. What I've done is I've zoomed in on a couple of these just because this is the full frame, and so obviously I had to compress the image there. So the next one, there we go, is the companion. This is NGC 5474, and it is a physical companion to M101, about the same distance. They're both about 20 million light years from here. And by the way, this image was a stack of 6 10-minute exposures. So this is classified as an irregular dwarf galaxy, and you can see this little guy here from the galaxy's catalog. This is not a related object. It is a galaxy, but it's only about 12 million light years from here. It's a dwarf galaxy that's not related to the M101 system at all. All right. The next one is, I believe, if I can get it to go. Oh, obviously a major malfunction. Chris?
I'm trying to.
You too? It was that supernova. That's what it was. She no work. Oh, there we go. Thank you. So this is M101 itself, pinwheel, a beautiful grand design spiral. That we're all familiar with, and again, it was more just a quick test shot to see what I could get with it. But what I was interested in was some of the neighboring stuff. I wanted to see how far down I would get because, as I said, the evening was very nice and clear, and the sky was very stable. So you can see a lot of the giant H2 regions kicking around here, especially this one up here. This is. NGC 5462, and I draw your attention to that because the next part of the image I'm going to show is up that way. So if we can go up there, oops, that went too far. Can you back up? Okay, well that's fine actually. Yeah. So again, here's the H2 region, M101. And this little guy is another companion. This, in fact, is the closest companion to M101. It's NGC 5477. And again, it's about 21 million light years from us here. You can just step through those, Chris. I think I just had a few of those labeled there. There we go. Yeah, there's the H2 region, and the next one just shows the galaxy itself. Okay. So this was all very nice, but what I did after that was I wanted to see what other galaxies I could see in this field, because this area is really rich in galaxies. There's a number of really small galaxies scattered through this entire region, and they're all part of the Ursa Major galaxy cluster and cloud. And so I just wanted to see, even with an 80 millimeter telescope, how far I was reaching. So the first group here shows this bunch, and they range in magnitude from about 16.4 for that guy there. These numbers are, by the way, from the PGC catalog designations. Range in magnitude from about 16.4 to 18.3. And distances here vary from about 93 million light years for our friend there to 238 million light years, and then up to 544 million or 588 million light years. So I thought, well, that's very cool. That's reaching out a fair ways with a relatively small telescope. So again, I examined the image, and I really dug into the PGC catalog for coordinates and just to see what else I could map out. So the next group, the next group really got me going. This is an interesting bunch here. I mean, there are only dots on this image because, again, the image scale is very large. It's a very small telescope, but these galaxies, this really kind of took me by surprise when I looked at the recessional velocity data that's available in that catalog, and I found that the recessional velocities for these galaxies are almost all identical. And when I ran the numbers on, I used that recessional velocity to calculate the distance. These galaxies are about 1.1 billion light years from here. And they're virtually all the same distance. So this whole complex, it's like a sheet of galaxies all at the same distance from us here. And I thought that's very cool, especially being as distant as they are. And then the last one that I took, there we go. This one really knocked my socks off because these guys, there's one up there as well. These guys, they range in magnitude from about 18.1 all the way up to 20.0. So we're talking really distant, dim galaxies. And when I ran the numbers on the recessional velocities to calculate the distance, I was just floored because these galaxies range in distance from 1.4 to 1.7 billion light years from Earth. That just blew me away. I didn't expect to be able to pick up those galaxies with that small of a scope, but it just makes me put up my hands and say, like, you got to marvel at the technology available to us as amateurs these days. It's really quite profound. So I can't wait to get that camera on my big scope, which is in the process of having an observatory built for it. So stay tuned. Hopefully I'll get some closer stuff on these and be able to show you some of that in a few months. So thank you. All right. Guess I'm flying. Are we good, Chris? Okay. Yeah. Does it work now? Oh, it does work. All right. Up next is Al Scott with his 10-minute astronomy news update. Take it away, Al.
So I wanted to start us off with a bang. I don't know. You've probably all heard about this this meteor that exploded over Chelyabinsk. It was a stony iron meteor that came into the atmosphere. They've actually had a lot of footage from various cameras of this event. It's actually they've now recovered fragments. There's a 1 kilogram fragment. It was a stony iron meteorite, about 10% iron. and they've been able to work the orbit of this thing back using footage from various cameras. It's an Apollo class asteroid that came in. So we've got some video of it. And so I just click, or do you want to do that? So imagine driving to work in the morning with your dashboard camera, and then you see that. Entering the atmosphere at about 18 kilometers per second. And glowing brighter than the sun. And here's the smoke trail of it. It actually there was a bit of a shock wave. There are multiple explosions. The explosion breakup was right directly over the city of Chelyabinsk, Russia. Over 1,000 people were injured by the glass. They actually were able to estimate the. Go back. Can you go back to the other slide? They're actually able to estimate the size of this from the infrasound, because they have infrasound listening posts set up around the globe, and the infrasound explosion carries, and they use these for tests for monitoring nuclear explosions, and so the explosive energy of this was around 500 kilotons. This was the largest known bolide since the Tunguska event over Russia back in the early 20th century. So really a big event. They estimate that the asteroid was about 15 meters in diameter and weighed about 10,000 tons. And there was a hole in the lake ice. They haven't actually recovered any big fragments yet, but they're looking. So now we'll go up the. Yeah.
I just heard Mitsu Keiku.
Mm-hmm.
He was on just the other night on Skin Colbert, and it was a few seconds later. It wouldn't have been a shockwave in the air. It actually hit the ground.
Wow. Yeah.
It hit the ground with the equivalent to 20 Hiroshima bombs.
Yeah, it was a very low angle of incidence, and they figure it exploded about 20 kilometers up. That's why there was such a delay between the sighting and the explosion shockwave. So in rapid response, Canada sent up 3 satellites. Or 4, actually. The week after, to hunt for near-Earth asteroids. This is amazing, really. It actually was not related, but a very good publicity for Canada's satellites that went up on an Indian rocket, the PSLV. There's in the left here is a model of the Sapphire instrument, which was a D&D camera on a Surrey bus, and this camera was built. The instrument was built by ComDev. The prime for the mission was MDA, and this is to actually look for satellites. It's a low Earth orbit. These are all polar orbiting now, around 800 kilometers altitude. And this one's to look up at the GeoArc and provide updates on the coordinates of these things to NORAD, who monitor all of these things and continually update the orbital elements of them. So this is Canada's contribution it's a military satellite to contribute to our part of NATO. The one on the bottom right is NEOSat. NEOSat is a combined DRDC science mission. So DRDC is a defense research establishment. It also has a mandate. Half of its mission is to look for orbital debris. The other half is to search for near-Earth objects, the NEO portion of the name. And the PI for this mission is Dr. Alan Hildebrand, who is a past president of our society here in Ottawa, actually. And this was actually it was supposed to be a build to print of Canada's most microsatellite. So it's very similar in size to the most satellite that's been up there doing astronomy. And this has got a big baffle. You can see the baffle pointing out at the end of it on the bottom right there, so that it can look very close to the sun and see asteroids that we wouldn't be able to see from Earth, where the atmospheric scatter of the sun's glow would make it impossible for us to see it. You have to go up into space to look very close to the sun to see these things on orbits that are interior to the Earth's orbit. There's very few of them that have actually been mapped because of this problem. You can't map them from the Earth. And in the upper right is the world's smallest astronomy satellites, the Bright constellation. And this is to look at very bright stars. And it's as you can see, it's a CubeSat. And there was 2 of them, and they're Austrian actually, but they were built by UTIUS, the University of Toronto Institute for Aerospace Studies. And they are they're going to stare at very bright stars and do astroseismology, measure the vibrations of these stars and learn about their interior workings. And there's going to be 4 of them in the constellation. There's 2 that were just sent up. So some interesting times ahead for Canada in terms of searching out asteroids and astronomy and cameras in space. So lots of interesting times ahead. Hopefully they're all working fine up there. Thank you.
Next speaker up, first-time speaker, is Mike Banks, who's going to give us a peek at some of the very cool facilities in Hawaii. So, Mike?
All right, so my wife and I were planning a trip to Hawaii before kids. So we planned that for a couple of years and brought along the in-laws. Basically, we went to Hawaii, and this is Honolulu right there. First stop was Pearl Harbor, of course. And for those of you that have seen the movie, you'll see that that's the control tower for Pearl Harbor. What was happening here is we actually got the Venus Transit. So you got some kids on the parking lot there looking up through little paper things that they provided. The astronomers all got together and had a public sky party, basically. So there's my wife looking up at the stars next to some Navy guys. It is an active military base. So they had some telescopes set up, and I managed to actually get a shot of the Venus Transit with my iPhone. I tried using my DSLR, but the sensor's too big, but I managed to do this. So you got Venus there. You can actually see some sunspots here if you look really closely, but it's pretty hard to just hold it just with your hands. Next stop, we flew over to the Big Island, which is called the Big Island because it's big. So Honolulu was right here. That's where we started. Then we flew all the way over here where this pin is dropped, and that's Mauna Kea. So when we got to the Big Island, you can basically see the observatories on the top from a lot of the island just because there's not many trees and it's very big. The ones that you see here are the Keck Observatory, and then there's Subaru right there. And as you can see, they're above the cloud base. So they're actually 14,000 feet up right there. And we're closer to sea level when the shot was taken. The next day, we spent the night in Hilo, and then the next day, we went up to where the astronomers have lunch. And so we had lunch with them, and this is at 10,000 feet, so you got to climatize. You can't just go up to 14,000 feet. You have to sort of settle down and let your body adapt to the altitude. So we had lunch, spent a couple hours at 10,000 feet. Most tourists actually stop here. There's a little tourist facility. They have a gift shop and a bunch of flyers and stuff like that. But we were fortunate enough to get in touch with a couple of the observatories, and they were nice enough to bring us up. So my wife, my mother-in-law, and Ed are in the background. He's the resident astronomer for the Canada-France-Hawaii telescope, and he was nice enough to offer us a drive up. The sound is the light, I think, but I don't know how.
Your right hand.
Right.
No, right hand. There's a button right under.
Oh. There you go. Better? I have an iPad, so I can see. All right, so the road up is actually kind of treacherous. It's actually very dangerous, especially in the winter when they get snow, which is interesting to think about snow in Hawaii. But anyway, you're not allowed to take rental cars up there normally, so these are actually cars for the observatories, SUVs. As you can see, it's very treacherous because you might actually go off the edge of the mountain and, well, that's game over for you. You'll notice the rumble strip in the middle of the road. That's so that they can grope their way down the hill or the mountain in a blizzard or in fog or in very inclement weather. So they literally just put the tires on the rumble strip and follow it all the way down and they can't see. The first observatory we saw was Gemini North. I say north because there are two of them, which I'll get to in a sec. So we got to the parking lot here. Gemini North is actually a very big place. And it's very cold up there. You'll notice we're putting on coats. Yeah. So it came into operation in 2000. Its twin is Gemini South in Chile. It has an 8.1 meter optical and infrared telescope. Together they observe the entire sky as the Earth rotates and as it goes around the sun. And they're built and operated by a bunch of countries, including Canada. This is the control room. So this is just one of the workstations. They can monitor remotely, but they also can monitor from the observatory itself. It's basically just a very nice computer setup. I was kind of envious. This is the telescope itself. I have Claude down there to give you a sense of scale. A lot of it is just open scaffolding, but the sensors live down here. The primary mirror is in here, and then it reflects down. The instruments. Oh, well, we're standing below it. I'll get to the instruments in a second. The entire telescope can rotate on this blue area. This whole blue area allows the whole telescope to turn, and it is anchored right to the mountain, so it's very stable. So we've got the instrument packages here. You'll see Altair. That's the Canadian one. It's an IR spectrometer. It's built by the Hertzberg Institute of Astrophysics. There's also on here, I don't know which ones are which because they're basically nondescript boxes, but there's NIRI, which is a near-infrared imager. That's from the University of Hawaii. There's NIFS, which is a near-infrared integral field spectrometer, and that's an Australian contribution. It's fed by Altair, so Altair feeds data to it. There's the GNIRS, which is a spectroscopy sensor, and then there's GMOS, which is the multi-object spectrograph. So they're all in there. The close-up of Altair with Canada's word mark there, and I believe last month somebody had some images taken by Altair, so there's the sensor that took those images. Next up was Canada, France, Hawaii. Very rare to go to Canada, France, Hawaii, so we were very fortunate to have that opportunity. It's a white dome instead of the silver dome from Gemini. And again, we're in the parking lot because we drove over to it. You don't do a lot of walking up at 14,000 feet. You get pretty lightheaded. So we started off in the parking lot, and there's Eder. And then we went to the clean room, which is below. It's basically the bottom of the building, kind of in the basement. This is where they clean the mirror, and this is where the mirror sits normally. This is the big bell jar, essentially. It's a vacuum chamber. It's where they vaporize the silver, or I think aluminum is what they might use now. So they put this over the mirror, and then they evacuate all the air, and then they mist in the metal to make the mirror all nice and shiny and clean again. And that's what the mirror gets covered up by. It goes underneath here to protect it when they're not using it. And you can see the crane. The mirror is very heavy, of course. It's very large. So this is the control room for CFHT. Now, it was built in the 70s, so it's not as fancy as the Gemini one, but it does the job, and it's all mostly remotely controlled now from sea level. There's a town where the astronomers actually live and do the observations from, so the telescope is basically fed onto the internet for them. As you can see, they're very interested in the weather because weather plays a huge role in the sky conditions. And they've got cameras all over the place so they can monitor what's going on outside. Recently they had a picture up on Facebook of, they had a blizzard, so it was complete whiteout. So all of these screens were basically white, even though they were looking outside. Skip one there. So yeah, as I mentioned, it became operational in 1979. It's an optical infrared telescope. Again, it's a bit smaller because it was biggest when it was built, but there you go, progress. It's the first large telescope built atop Mauna Kea. The other one was built by the University of Hawaii, and it's a much smaller one. I'll show you a picture of that later on. The three main instruments on the CFHT is the Megacam, the WIRCam, and the AOB PUEO. I'll get to those in a second. So that's the CFHT. I've color corrected it because the lighting in there wasn't the best. Basically, this yellow thing is a giant equatorial, which holds the telescope sort of down the middle of it there. So have that in your backyard, it'd be pretty neat. Note the door that you can go inside of it to give you a sense of scale. So there we are standing underneath it. My father-in-law mentioned that during one of the earthquakes they had a few years ago, the entire telescope assembly was weightless for a fraction of a second, and then it came crashing down and broke some stuff. So there you go. But yeah, so we're underneath it, and those are all the instruments. Close-up of the instruments. So what you've got here, I'll show you Megacam in a second. That's at the top. But there's the WIRCam, which is a wide-field infrared camera. It's designed to complement the Megacam, and it's fitted to the prime focus when there's a full moon, and dark times are for Megacam. So that's off to the side right now because they had the Megacam fitted up top. There's a ESPADNOS. It's a bit of a tortured acronym. But it's the Echelle spectropolarimetric device for observing the stars, and it observes the complete optical spectrum from 370 nanometers up to 1050 nanometers in a single image. It's bench mounted downstairs in a black room, so it's on a big table basically. We didn't get to see too much of that one. So this here is one of the original observing stations. Basically, the astronomer would seal himself in here with film and sit up top and stay there basically until the exposure was done, which could take hours, and it was freezing up there. So they would basically, this is Megacam, but they would fit that, so they would fit this up there. And so the astronomer would climb up and hang out in there while the exposure was happening, and he couldn't move very much, or he would risk making it blurry. So we've got Megacam up there now, which is a giant CCD. It's a wide-field optical imager. In 2003, it was the largest astronomical CCD mosaic ever built. It is 340 megapixels, covering 1 square degree field of view. So it's pretty big. And then the WIRCam fits on there when the moon's out, because it just looks at infrared. So there we are, standing underneath the telescope. It was, just to give you a sense of size. We got to go on the catwalk, which was kind of neat, because not many people get to do that. But Eder was nice enough to let us go there. So you can see there's Gemini next door, and then that is the University of Hawaii's telescope. So just give me a second here. I'll catch up in my notes. So yeah, we just got to walk around. It was pretty windy and a little bit cold, but as you can see, the sky was nice and clear on this side of the mountain. These telescopes occupy the best spots on Mauna Kea. And the other part of Mauna Kea is occupied by these telescopes. So what we've got here is we've got the Subaru Observatory. That's the Japanese. We've got the Keck 1 and 2 observatories there. And we've got the NASA observatory. It's the infrared observatory. So Subaru has an 8.2 meter dish, or mirror, and it's the flagship of Japan. It was completed in 1998, and it looks for exoplanets at the moment. The Keck can operate together or individually, and when they operate together, they form a single astronomical interferometer. They each have a 10-meter diameter optical imager. And NASA has a 3-meter telescope, and it's optimized for the infrared, and it was built to support Voyager when they launched the Voyager missions.
I have a question. Can they be combined as an array?
The 4 of them, or just Keck?
Oh, yeah.
I don't believe so. The two that are Keck can, but and they're actually working on combining CFHT, which is the white one here, and the Gemini. They're working on that, combining those two right now. But as far as I know, those are the only 2 that they can combine at the moment. This is the not the best side of the mountain because that's the windward side. So what happens is you get the warm air off the ocean riding up the side of the mountain, and you can see the clouds are building there, and there's always sort of cloud cover during the daytime as the solar heating happens. Subaru was nice enough to open up its doors for us so we could peek inside. So I like this shot. This is kind of neat. And the little helmet. This is my wife's favorite telescope because it looks like a cute little helmet. You can see there's a van here, so that gives you a sense of scale. It's not so big. What that is the James Clerk Maxwell millimeter wave telescope. So she likes it because just the way the door opens is a little cute. Looking back as we're on our way down again, so you've got the CFHT here. There's the weather station that monitors all the weather. You can't really see it here, but there's a conduit connecting Gemini and CFHT for that experiment where they're connecting the two. Of course, that's Gemini, and that's the University of Hawaii's telescope. If you want to visit Mauna Kea, Gemini is actually, they have a pretty good outreach program. Here's the link if you want to take it down. Otherwise, CFHT also has outreach, but they're a bit more restricted. And there's the link there. You can ask me later if you'd like the links. They have a bunch of information on their websites for contacting them and whatnot. And of course, in Hawaii, we had to go scuba diving, so I thought it's middle of winter, why not throw in some scuba pictures? So this is a nice sea turtle we caught down there while we were diving. And of course, we saw a volcano as well in Volcano National Park. Thank you. So that's my quick little introductory to Mauna Kea.
That's great. Thank you. Well, thanks for sharing that with us, Mike. That's some really nice imagery there, a nice quality on the shots.
Thanks.
Excellent. All right, we're almost at the end. We're going to have one more quick talk. Chuck is going to talk to us about, let me think now. Oh, well, you can surprise me.
Thanks, Paul. The laser's working? There we go. Yeah, I'm standing between Rick and his beer, so I won't be too long. Where are we here? Okay. So, Yellowknife, Al, Julie and I just came down from there, and I'll give you a quick rendition of what we did. But first, as your impact crater coordinator, I'm pleased to report that, yes, we have one new crater on this planet. Al described the whole situation that happened, so yeah, it was quite the surprise. And those shock waves, the big one and then the tiny ones after were pretty impressive. I like that. Okay, so I'm going to describe one of the last sets of craters that we've explored, Pilot Lake, just in the southern part of Northwest Territories. I'm going to start our trip, though. We started up here at Tuktoyaktuk. I'm going to show you Great Bear Lake, Lake de Gras, and Yellowknife at Great Slave Lake. But first, whoops, where are we here? Will this work?
Your dot came up.
Oh, yeah, there we are. Just, yeah, 445 million years. Basically, the first moss was on our planet at this time when Pilot Lake happened. And where did it happen? Right there. That's what we looked like 445 million years ago. Anyway, Tuktoyaktuk. Now you have to look here. Here we're in the northern hemisphere. We're looking at the sun, and the sun is due north. Kind of weird. The shadows pointing due south, and in the background are the pingos. We went up there to see the northern lights, but nobody told us the sun didn't go down. Anyway, off from Tuktoyaktuk heading south, Great Bear Lake. This is Lake de Gras, halfway between Great Bear Lake and Great Slave Lake. These are diamond mines. $1 million a day comes out of each one of those holes. Awesome stuff. That's almost 3/4 of a mile deep, those craters. And it's in a lake. They had to make a dam to dig these holes. This here is Great Slave Lake, just to the east of Yellowknife, and the cliffs are awesome. I took a whole series of images there, but it was good eye candy on the way down. So Pilot Lake. This is the impact crater 445 million years ago. Great Slave Lake, Lake Athabasca, the Sand Dune Park. They call it Pilot Lake because probably we have all seen the Buffalo Airways series of flights up from Yellowknife. You think of it yourself as a bush pilot coming from Fort Money, I like to call it, Fort. And up to Yellowknife. The lakes, you got a big lake here, but then between the two, it's pretty well all the same. So the only beacon pretty well is this round lake. They called it Pilot Lake, and I didn't realize it was a crater until just recently. As you can see, we're heading south at this point. Ottawa, if you stand on your tiptoes, you might be able to see it just over there. And you notice that the lakes, they all look the same up there, except for this big round thing. Now, the crater itself, 6 kilometers diameter. The lake is 90 meters deep. It's it's the deepest lake up there. This is what gave them the hint that it could possibly be a crater. So as we approach it, you can see that, yeah, it is pretty big. It is a central peak complex crater. It's 90 meters underwater, unfortunately. And we just took off from Yellowknife very early in the morning because we were up there with a group of other airplanes. There's 100 other airplanes up there. And it was the last part of the convention, and you can imagine a small airport like Yellowknife with 100 airplanes trying to get off. So Jillian and I, we got up at just after 5, I think, and we were the first airplane out, so we could do a nice tourist trip. And looking back north of, there's a big hole in the ground, that's for sure. Flying over Lake Athabasca, and these are the sand dunes just to the south of Lake Athabasca, kind of a neat tourist eye candy piece on the way down. And this is Carswell Crater, just to the south of the sand dunes. I described this a couple of months ago. And a very, very large crater, but of course it's buried. And now we're heading south, just south of Calgary, to the last crater, Eagle Butte, it's called. This happened just 65.5 million years ago, just after the great extinction of the dinosaurs. So a lot of stuff was happening there. And we actually had a couple of other craters in Saskatchewan around this time, and kind of an interesting sequence that happened. But Eagle Butte, 65 million years ago, Deccan Traps were going full blast, the volcanoes over there. The Rocky Mountains were just starting to form, and of course the Atlantic Ocean was just splitting apart. This is the rim of the crater. It's under the prairie, so unfortunately we can't see it, but being a fanatic on craters, I had to fly over it. And point 0 of the impact itself. So this crater represents now basically I've documented every crater in Canada except for 3. 2 of them I can't get to from the airplane, it's just out of range. And one, Jillian and I are eventually going to do it. It's up in the Northwest Territories, but it was way out of range was for this trip. So, in conclusion, this is the shatter cone we got. I got this from another member in Calgary. He actually footed it down to Eagle Butte. And a shatter cone is one of the firm confirmations in the fact that it is an impact. This is a crack or a shattering part of a rock, and the only way to get this is with a very high energy impact. Another energy impact that would cause a shatter cone is a nuclear explosion. So we're pretty well sure that it was a bolide impact, because we don't think the dinosaurs had nuclear weapons at that time. If they had a space program, they might have survived, but there you go. This actually is the sound sampling through the prairie regolith. It's about 50 meters deep. The crater itself is pretty pristine, but unfortunately it's under the ground. But the drilling of it did give some excellent samples, breccias and so on. So anyway, to conclude, my favorite slide here, how bright and beautiful a comet is as it flies past our comet. It's a quote from Isaac Asimov. But providing it does fly past us, this is the meteorite that Al just described to us, and a satellite view. And this was the very low angle impact. And as Gary mentioned, if it was a few seconds either side, it could have been a more of a direct impact, which would have caused maybe a bigger crater than I described earlier. Anyway, thank you very much. Less than 10 minutes?
Oh, yeah, I think you're good. Well, thanks, Chuck. Well, having visited almost every crater in Canada, plus the imaging you've done, you should think about writing a book. Seriously. Yeah, I think so. All right, just in closing, we have a few bits and pieces for you. First up, Sylvie.
Now that everybody is ready to fall asleep, I'm up again this month and next month to advertise the fact that the Canadian Space Society is going to host again a URI's night this year on the 12th of April. And they have asked us if we could come up with a couple of volunteers and have a table inside. No telescope needed, but a table inside to do some promotion. I think it would be a great opportunity for the RAS to get some exposure there at the Aviation Museum. So I announced it last month. I sent out an email, but so far nobody has shown any interest of helping. And if nobody does, we will have to cancel. So please, if you are free, it could be during the day or it could be during the night. Do let me know, email or catch me after the meeting before I leave, and we will set up something for them. Thanks.
Super. Thank you. Thanks, Sylvie.
You're welcome.
All right, and our usual closing notes. Estelle is here tonight, and so the library will be open. Her may or may not be.
It was open.
Oh.
Somebody closed it on us, and we're trying to get it open again. So we'll
Okay,
see.
may or may not be open. All right.
I'll accept any returns.
All right. Nevertheless, Hubble's Universe is Estelle's pick of the month there. And as usual, we have our post-meeting entertainment over at Kelsey's there. Estelle, as I just mentioned, will be here hopefully to open up the library. Al Scott is here, and if you're interested in perhaps borrowing a telescope for a little while, go see Al. Our usual coffee and conversation out in the lobby with Art and Ann. As well, you can see Art for RASC membership info and membership cards. And you can email Stephen, yes, for Sky and Tele and Astronomy renewals. The rest of the museum is closed, and you're welcome to join the diehards over at Kelsey's, where Rick Wagner will lead us in a solar graph building project. Yeah. Right, Rick?
Bring your tools.
All right, we had 122 folks tonight. Thanks for coming, much appreciated. Thanks for everybody that contributed, imagery and talks, and to the museum for hosting us. Comments and complaints, moi. And next meeting, April the 5th. So April the 5th, usual time, and hope to see you then. And remember, 10 days from now, the comet is coming. So hopefully we'll get some cool imagery next meeting, and we'll cross our fingers and hope at least we get some clear skies. Be safe, be happy, and we'll see you in a month.